Hello everyone, and thanks for joining me for this presentation on channel concentration and reflections from dredge channels. My name's Ben Modra. I'm a Principal Engineer with the Water Research Laboratory of the University of New South Wales. I'd like to thank my co-authors, Dan Howe, also from WRL, Anthony Folan from Mach, and Kate McLean from the Port of Townsville. This study was conducted for the Port of Townsville, who were looking to conduct capital dredging to expand Platypus Channel, which is the approach channel into the Port of Townsville. To dispose of the dredge spoils, they planned to create a land reclamation extending the port, and the land reclamation needed a seawall to protect it from the ocean storms. SMEC was designed or commissioned to design the seawall bund, and WRL was commissioned to conduct physical modelling of the design, including 2D and 3D and quasi-3D modelling for stability. And the focus of this presentation, a 3D physical modelling study of wave transformation into the bund. Now, the reason why the study was conducted, the 3D model study was conducted, was to investigate possibility of wave reflections from the dredge channel and the Berth 11 dredge pocket interacting constructively with the incident wave climate to create a larger design wave height. Now, this is something that has actually been observed at the site. Lex Nielsen was there in 2009, and he observed that the wave height in the lee of the Berth 11 dredge pocket was much lower than that to the southeast, where there was much stronger wave action against the seawall. Channel reflection is quite well understood in coastal engineering, and there's quite a lot of research on it. It's beautifully analogous to the total internal reflection of light. But both phenomena, it's related to the celerity of the wave as it's propagating through different media or in different depths, as the case is for coastal engineering. As coastal engineers, we're used to looking at wave refraction as it approaches shallower water, becoming more normal to the contours. Of course, as waves go the opposite way, as you go from shallow water to deep water, it refracts away from the normal. If you make that incident wave angle wide enough, you actually get reflection off that boundary. And for dredge channels, that nice straight boundary makes quite a nicely defined reflection. There's a really good example in nature. This is Nazare, which is regarded as one of the biggest wave surf spots in the world. You can see here the waves approaching from the right of screen. They reflect off the channel boundary over here and create this reflected wave, which then combines with the incident wave and shoaling to create a very large wave height. If we look at the bathymetry at Nazare, we can see why this is the case. Waves approach here from the northwest. They approach the straight channel edge here, reflect, and create this very large wave over here. So back to our model study. We conducted the modelling at 1 to 100 scale, which is certainly large enough to get to measure the wave heights that we needed to in the model. You can see here the waves generated at the top of the screen, pushing down across the bathymetry towards our bund structure down here. This is the bathymetry was constructed in the model, and we're looking at how the waves may transform off the edge of this boundary here into our model. We've got a series of probes, reference probes as our deep water probes here, probes along the channel, at the bund, and inside the channel. This 7-probe array here was particularly useful in looking at the directionality of the wave, being able to resolve the incident wave height and the transformed wave across here. We included reflection damping all around the edge of the model and some damping here to ensure that energy wasn't being pushed into the channel. You can see a photo of the setup. We've got our wave paddle, platypus channel over here, berth 11 dredge pocket, our bund, where we're interested in our wave height, wave probes throughout the model. Wave conditions that we tested, as mentioned before, were cyclonic waves. They were developed by Mid-Ocean Solutions. The cyclone included a long period peak energy and a second peak of high frequency waves, which is the wind sea state that's developed inside the Great Barrier Reef. 7 probe array, as I mentioned before. There's a close-up look at it. This, I think, is the first time directional wave spectra has been developed inside a basin in Australia. You certainly see some cases overseas, different configurations of probes, but I found this to work quite well and quite similar to a 3 probe array, which is used in a flume. So what happened when we set up and ran this model? Well, here's monochromatic waves. We're expecting reflection. This is a channel boundary here. We're expecting reflection back out here, but we don't see that. What we see instead is the waves squaring up to the edge of the channel boundary, building in wave height to the point of breaking, and almost no reflection of energy back out into the shallow water. Here's another angle. This is low. You can see the channel boundary here, wave breaking through here, and you can't really tell about the reflection out here, but there isn't much. Here's another one, the same condition, just slightly more energy to increase the breaking earlier. And we can see that now that we've got that the wave squares up and breaks. No release of energy out here. Well, there is a little. There's a secondary short period wave that's created to do with the wave breaking. So this was really unusual. I'd never heard of this before. And I spent a lot of time looking to try and find out if anybody had recorded this or researched this process. And it took a while because I didn't know what it was called, but I eventually stumbled across this paper by Swanborn and Grieve, where they're looking at the Richards Bay Harbour, which was being constructed at that time, or designed at that time. And they observed this effect that they called channel concentration. So here you can see the identifying refraction and refraction here and channel concentration through there. So why do we have this effect? Why do we have this building up of energy along our channel boundary? Well, a clue might be in Mach stem reflection. And this is something that's been known about in coastal engineering for quite some time. Normally, if a wave approaches a vertical wall, it reflects off it almost perfectly with very little energy loss. If you reduce the angle of incidence down to a very small angle below 20 degrees, instead of reflecting away from the wall, you get this Mach stem effect. And that is a building up of energy against the wall and almost no reflection. Sounds very familiar. And I see this as really a complex interaction between two waves at a shallow angle. So let's have a look at a couple more cases. Let's explore it a little deeper. This is a short period wave, and again, we see the same effect, squaring up of the wave, almost no reflection back into the shallow water, but we do see a bit more energy crossing that boundary out there. So the effect is less pronounced with shorter periods, as we might expect. Here we can see one of our actual cyclonic test cases. We've got a long period energy, which tends to build and break along or concentrate and break along the channel boundary, and the shorter period energy, which largely passes across our boundary. That short period peak is about 5 seconds. Here's another location of the model. This is the berth 11 dredge pocket with platypus channel up this way, and our bund over here. Here we can see the wave energy, incident waves coming in this way, and we can see this reflected energy off of the berth 11 dredge pocket, creating a classic diamond pattern associated with channel reflection. Now, normally this location here, down here at the bund return, would be quite well protected from the wave energy here. We just see some diffraction into this area. Instead, we have quite a strong amount of energy being redirected here by the dredge pocket. And we'll have a look at some of the results from our wave probes. These numbers here are the wave, the ratio to the deep water wave height. So clearly 1:1 at our deep water probes, increasing wave height across our channel boundary. This one here, that's largely consistent with what we had from the 2D model, where you get some reduction in wave energy as it propagates across this bathymetry. This here, region here, would otherwise be largely protected, but is seeing quite a high wave climate here by comparison. This was one of the key outcomes of the modelling. This area here, which could have been engineered with a slightly smaller armour size, actually needed the same armour size as the rest of the structure, the front seaward facing side of the structure. This is our 7 probe array here. Our results from that show our incident wave climate, which is our long period peak of our energy spectra, plus our shorter period wind waves through here. That's coming in at an angle of 30 degrees, and our transformed waves, where only the longer period energy is redirected back towards the structure. So in conclusion, I hope I've convinced you that channel concentration and channel reflection are important processes to consider anywhere we have dredged channels or dramatic bathymetric changes. And there's a real need to develop some guidelines on wave growth, critical angles, and the width of influence of the channel concentration. Thank you.